Alright, so for this particular problem, we have a mass of 1.22 kilogram. It's pushed against the spring, so it's going to push the spring leftward here, compressing it. The spring constant is 450 as stated, and it is compressing the spring a length of 0.24 meters to the left. And it says when the block is released, it's going to shoot and it's going to go up the ramp, and the ramp here is 37 degrees. Alright, other than that, let's go and crack it out. A, B, C, and D. Part A wants us to find what is the speed of the block as it slides along the horizontal surface after having left the spring. So essentially, once the spring fully uncompresses, it's going to shoot this box out at a certain speed. What is that speed? Alright, so let's go ahead and do it. In order to do this one, I'm just going to set up conservation of mechanical energy. So here's the V that we're trying to find. So once again, you have to visualize this red box push leftward, and then once it's let go, the spring will push it rightward, and then by the time it gets to where it was initially, it's going to shoot out at a certain speed. So there's my V, then question mark. So here I'm just going to set up conservation of mechanical energy. So generically, mechanical energy for a conservative system here, I'm just going to write all the terms out. So if you need to, this second line here is pretty helpful in terms of practicing stuff out. This is PE due to gravity, which depends on height. This is PES due to the spring. KE here is kinetic energy initially. And then here on the right side, this is just your final reference frame. So initially it's compressed, and then finally it's uncompressed. So here is P due to gravity, PE due to spring, and then KEF. But you notice here I'm going to write things out, but then I'm going to start crossing things out where it doesn't exist. PE gravity I'm going to cross out because the box is on the horizontal surface. There's no height. PE spring I'll keep because that is where the energy is initially coming from. So whatever's doing the pushing is going to create work because pushing it left has an applied force, and then pushing it left imply that the box is going to go leftward. So anytime you have a force and a displacement, there's work done, and that work is stored in the spring. So PE spring exists because once you let it go, that energy gets converted to KE. KEI here I'm going to cross out because KEI is 0 because the box is being held, and then it will be let go. So initially it's at rest. Likewise on the right side, PE gravity at this point here, after the spring has fully uncompressed, the box is at the same height level or on the ground still. So there is no height involved. So I'm going to cross out PE due to gravity because it depends on height. The PE spring I'm also going to cross out because, well, the spring has fully uncompressed. So there's no energy stored in the spring. All that energy that's stored in the spring will now be converted to kinetic energy. KEF now exists because now the box is moving at maximum speed. All right, so I'm going to break up PE spring initially as 1/2 kx squared. That's the function for PE due to the spring. And then on the right side, likewise, 1/2 mvf squared, vf being this v in purple in the diagram because that is my reference frame to start the problem. So here's the initial over here, and then this is my final reference frame. Okay, you notice here 1/2 appears on both sides, so I'm going to cross that out. So to solve for the speed, vf here, I'm just going to go ahead and divide both sides by m. So this m here, I'm just going to move it down to the bottom left. So, but this is vf squared. It's therefore to get vf by itself, square root both sides. So once again, the first step is to divide both sides by m. There's that m. And then to get vf by itself, radical both sides to get rid of this exponent 2. So therefore, I'm just going to plug in value, k being 450, x being 0.24. We're going to square that. And then mass being 1.2. So if you plug in that into the calculator and then square root all that, you should get a value of about 4.65. Okay. So the speed here at this point, by the time it fully uncompresses, is 4.65 meters per second. Because it asks for speed, I'm just going to leave the answer as is. If it asks for velocity, according to the diagram, it would be 4.65 meters to the right, or positive 4.65. Make sure you include directions where and when appropriate. All right. Here, part B asks us, how far L does the object travel up the incline before sliding back down? So here's the length of the ramp. Well, it says before sliding back down, imply that at some point the box is going to have to come to a stop before it changes direction. So that is an important condition. So let's go ahead and crack out part B. Here I call this HF because this is the final height. The box eventually will rise to some height before it comes back down. Well, what I can do is I can find height, and once I know height, I can find L because this is just a triangle. The angle is given, so to find L, all I need is one of the legs. Here in this case, I can find H because there's energy involved, so there's height involved. All right, so I'm going to go ahead and set up conservation of mechanical energy again. Once again, I'm just going to carry the second line down just to help you practice here. PE due to gravity, plus P due to the spring, plus KE. So I'm going to start from the very, very beginning of the problem when the spring is initially compressed. So all that energy got converted to KE, and all the KE will be converted to potential energy due to gravity. But I'm going to choose to start from the very, very beginning when the spring was compressed. If you want, you can actually use the KE here once it's uncompressed. That's up to you. It doesn't really matter. It should all work out the same. So here, I'm going to cross out PE due to gravity because there's no height initially when the spring was compressed because it's on the floor. A PE spring does exist. KE crosses out because it was initially at rest. Here on the right side, once the box gets to the very, very top of the ramp, there is no more energy due to the spring because all that energy has been converted. Here, KF I'm going to cross out because in order to turn around, you have to come to a stop momentarily, which implies that the final speed at the top of the ramp is 0. So I'm going to cross out KEF because it depends on speed, and speed is 0 at the top of the ramp. All right, on that, you notice here, I just have PE due to the spring is equal to PE due to gravity, which makes sense, right? This is a conservative system, so all the energy that was initially compressed in the spring, stored in the spring, is going to transfer to kinetic, and all that kinetic will now be converted to PE due to gravity. So it changes forms as it travels up the motion. All right, so here I'm just going to break up, once again, PE spring to just 1/2 kx squared. PE due to gravity is just mghf, hf being in the diagram here, whatever this height is that will cause the box to momentarily come to a stop. So here, to find hf, I'm going to divide both sides by m and g. I need hf because once I know hf, I can find the length of the ramp, all right, the hypotenuse of the ramp. All right, so to get hf by itself, once again, divide both sides by m and g. So here on the top, we have kx squared, which I carry down. The 2 is in the denominator, and since you're going to move the m and the g down to the bottom left by dividing both sides by mg, it looks like 2mg. Here, we just plug and chug. All right, k being 450, x being 0.24, we're going to square that. And then the 2 is part of the function, and the mass is 1.2. And then here, g is positive 9.8 because we're just dealing with energy, which is a scalar quantity. If you simplify the numerator, you get 25.92. If you simplify the denominator properly, you get 23.52. Simplifying that down will give us a height of 1.1. Now, we're not done yet, right? We weren't asked to find h. We're asked to find the length of the ramp. So therefore, all we have to do is do a little geometry. I'm going to apply sine here because sine by definition is opposite over hypotenuse. Well, the angle here is 37. I just found HF, which is my opposite leg. And then I'm asked to find L, which is my hypotenuse. Hence, sine is opposite over height. Well, I'm using that because I know theta is 37. My opposite is HF. And then the length of the hypotenuse is just called L. Here, to solve for L, move L up to the top left or multiply both sides. And at the same time, divide both sides by sine 37, which I'm just going to move from top left to bottom right. So here, we have HF already. We can just plug it in. And then, well, you plug in 1.1 divided by sine at 37 degrees. You should get a length of about 1.83 meters. So that is your answer for part B. Now, if you want to, you can attack part B using a different strategy. So I'm going to do for you just to hopefully help you, build confidence and give you extra practice. The work kinetic energy theorem applies, for all types of scenario, right, with or without friction. So here, I'm going to write net work is equal to change kinetic energy. Well, here's the box. By the way, I'm just going to draw a box on the ramp just to show you where the force and force components are going. Here's f of g. F of g points down. So while it is going up the ramp, there has to be some sort of force acting on it because the object decelerated, right? It was moving at a speed of 4.65 at the bottom here, and then it comes to a stop. So which imply that there is an acceleration, or if there's an acceleration, there has to be some sort of force acting on it. But here on the ramp, this is f of g, this is f of gy, and then this is f of gx. Okay. Now f of gx is fg sine theta. It's sine because this is the opposite leg from this angle. So this angle here, theta in blue, is the same as the angle of the incline, which is 37 degrees. So if you've done your incline problems, all this stuff here is just review. If you haven't, it's important that you learn how to draw a right triangle. So f of g being your hypotenuse, f of gy, and then here's f of gx pointing down slope, right? But by definition, f of gx is just the hypotenuse, which is f of g times sine because it's the opposite leg. Now, we also know that f of g by definition is mg. Keep that in mind. All right, so in order to do work, though, I made a comment here, right, that it's important for you to, keep in mind that you need the force component that is parallel to the displacement. So the box is moving up the ramp, which is now your x-axis, while the component that is parallel to the ramp is this f of gx that I have emphasized here in large here, okay? So once again, you need f of gx, but f of gx is going to point down slope while the box is going up slope. So the only force component that I need is f of gx, because f of gx parallels the surface of the ramp. And the surface of the ramp here is called L, so really which is the same as delta x. So I'm going to break it up. Oh, kf I'm going to cross out because I said it earlier over here, right? It has to come to a stop, so kf is just 0. Here, f of gx is just mg sine theta. It's mg sine theta because f of g is mass times gravity, and then sine of theta is carried down. Here, I replace delta x with L because in this diagram, instead of calling it delta x, they just call the length of the ramp L. I'm just going to go with the variables given. Ki on the left side is going to be 1/2 mvi squared, so keep this in mind. I'm going to ignore the negative sign here because I'm just finding the length of the ramp, so it's entirely up to you. And then g here, you can plug a negative, okay? All right, so I'm just going to cross m's out because it appears on both sides. So here, if you were to solve for L, which is just the length, which cannot be negative because this length is distance. So to get L by itself, I'm just going to go ahead and divide both sides by g and sine theta. So here we have vi squared, which I carry down. The 2 is in the denominator. And then because I'm going to move g and sine theta to the bottom right, it looks like 2g sine theta. And therefore, if you plug this in, you'll get a value of 1.83. Okay, I do want to point out that the negative sign here, if you carry it down, it'll cancel out this negative sign. So the length here would just simply be 1.83. So this way, if you're sloppy with your negative sign, whatever, it doesn't really harm you because you're not adding or you're not adding or subtracting by anything else. So, so keep that in mind. All right. So my point is that you can use the work kinetic energy theorem to find the same length, which turns out to be the same 1.83 as we calculated here on the bottom right. All right. Let's go ahead and do C and D. Okay. C. It's just calculate the magnitude of the acceleration of the block as it travels up the incline. So here I can use kinematics. Vf squared minus vi squared equals 2a delta x. I'm going to cross out Vf because Vf is 0 at the top of the ramp. Vi being 4.65 because that's what I calculated earlier in part A, I think. All right, so here I'm just going to carry the 2, the A, delta x. Once again, I'm just going to replace with delta L because this is now on the ramp, which is just the length of L. So to find A, I'm going to divide both sides by 2n L. Therefore, it'd be negative Vi squared divided by 2L. So here, I'm just going to plug values in. The negative sign I'm just going to carry down. Vi being a positive 4.65 because it's moving to the right. I want to square that. And then the length here, once again, is a positive 1.83 because it's just length. And if you do this correctly, you'll get a negative value of 5.91. Now, this answer makes sense to me because, well, the only force that's acting on the box along the surface of the ramp is f of gx. And f of gx points downslope. So therefore, this answer must be consistent with that. So I'm going to say downslope here is negative because the line of motion up the ramp is positive. All right, other than that, the answer here is 5.91. Since it says magnitude, I'm just going to actually just go ahead and say that's 5.91 meters per second squared. So if it didn't say magnitude, the answer here would be negative 5.91. Okay, so as usual, make sure you understand what's being asked. So absolute value, 5.91. Part Oh, excuse me. Before I move on to part D, part C, if you wanted to, you can totally do Newton's second law, net force equals to max. But then if you look at the diagram once again, the only horizontal component that acts along the surface of the ramp is f of gx. Now I replace f of x with just f of gx because it is the only force in the x direction. And then I can break up f of gx into f of g sine theta, which is in the diagram here. And then I can break up f of g into mg sine theta. And as you can see here, mass cancels out. So the only thing I need is g and sine of theta. Theta is given as 37. So therefore, if you plug this in, g being negative 9.8, sine of 37, and so you'll get the same answer as negative 5.9 meters per second squared. But just give the absolute value because it says magnitude. All right, there's a couple different ways there for you to do part C. Let's do part D. Part D asks you to find the time it takes to travel the whole entire length L. Here, under constant acceleration. So this problem here, there's no additional varying forces, so the acceleration is constant. Because acceleration is constant, I can apply the average velocity functions equal to each other. So here, average velocity by definition is displacement over change in time, and then average velocity under constant acceleration can also be calculated using Vf plus Vi divided by 2. Here, to solve for t, because the question asks you to find time, t is the denominator. I've done this trick before if you've seen my other videos. I'm going to cross Vf out. I'm going to flip both sides because delta t is in the bottom. I'm going to flip the whole function, both sides upside down. So delta t now goes on top. Delta x goes on the bottom. The 2 now goes on top. Vi now goes on the bottom. And then to get delta t by itself, I'm just going to multiply both sides by delta x. So really, but delta x here is just L. Keep that in mind. So here, delta t is simply 2 times delta x, but delta x I replace with L. Vi stays on the bottom. L here being 1.83, Vi here being 4.65, and then if you simplify that problem in your calculator, you should get about 0.79 seconds. Okay, that is the answer to part D. Now, if you wanted to, you can simply just use the average acceleration equation. Average acceleration by definition is the change in velocity, which is Vf minus Vi over change in time. Here, we're solving for delta t. So I need to get delta t by itself. I need to get rid of a. So I'm just going to do a little quick switcheroo. Multiply both sides by delta t, but at the same time divide both sides by a. So really it's the same thing as switching these two. So I'm going to move delta t up to the top left, move a down. So therefore we have Vf minus Vi divided by a. But once again, Vf is 0, right? Because it has to come to a stop at the very, very peak there or top of the ramp. Vi, I know is 4.65, the negative sign I carry down. A being negative for the actual variable itself. Therefore, the negative signs cancels out. So if you take 4.65 divided by 5.91, you will get an answer of 0.79, which is the same answer as the previous strategy. As you can see, there's different ways to get these values. Hopefully, as you practice, pick a strategy that works best for you, okay? All right, stay nerdy, don't be whack.